Let's do a pretty short video on what's called a Pythagorean identity for sine and cosine. So an identity is an equation that's always true, like a plus b quantity squared is a squared plus 2ab plus b squared, things like that. And really important fact about sine and cosine that we can get as a consequence of Pythagoras. So we actually did this. It was kind of quickish toward the end of class one time a few days ago, but I really want to make sure we look at this again. And then it's going to be used in, crucially, in the derivation of the law of cosines, which I'm going to pair with this video. So let's just look at a very explicit example. It does not have to be any particularly nice numbers, doesn't have to be integers, a Pythagorean triple, but just to make things really pretty chill, I'm going to use a Pythagorean triple here. And we're going to look at sine and cosine, specifically of angle B. We could totally use angle C, but it really wouldn't give us anything new. And we're going to generalize in a minute. So sine of B, hopefully I think that's probably pretty confident right now. That's just going to be 5 over 13. Cosine of B, that's going to be 12 over 13. So opposite over hypotenuse, adjacent over hypotenuse. And then I'm going to do something that I'm going to take the sine of B, square it, and I'm going to take the cosine of B and square it. And what are we going to get? We're going to get 5 over 13. Whoops, that didn't go in the right place. We're going to get 5 over 13 all squared plus 12 over 13 all squared. And I'm not going to go to the calculator. If we did, we would still discover this, but it's much better to not go to the calculator at this point. Even though these are numbers, I'm going to think about it algebraically and say, okay, that's 5 squared over 13 squared. Very common thing. A quantity, either product or quotient squared, that square does go onto these factors. This is something where powers and products and quotients do play nice with each other, so we do have a good rule. Same over here, 12 squared over 13 squared. Wow, those are over common denominator. Okay. And now wait a minute. Does that look familiar? Let's see. Let's just get the numbers at this point. 25 plus 144 over 169. Actually, let me just keep going down. Well, that's coincidence. What an amazing coincidence. It's 169 over 169. Not working. Which equals 1. But of course, it's not a coincidence. This is Pythagoras, the fact that the top was exactly just a leg squared plus a leg squared. And we know that has to be hypotenuse squared. This is always going to work. And the claim is this is always going to equal 1. Okay, so let me show you with letters. I mean, I think that actually one example is fairly convincing because we're like, oh, it just worked because of Pythagoras. But let's see a little more official derivation with some letters, but we won't take too long on it. Okay, now it's renamed with letters, and we're using two standard conventions that we often call the two legs A and B and the hypotenuse C, but also in the very standard convention is we are pairing the capital letter name of each vertex with the lowercase name of the opposite side. And so we use that a lot in this business, okay? So in terms of that, sine of angle B, that is B over C. Cosine, still in math mode, cosine of angle B is just going to be A over C. Just exactly the same, just turning those numbers into letters. And we're going to do the same thing. We're going to take sine of B, and we're going to square it. And we're going to take cosine of B, and we're going to square it. And that's going to be the quantity B over C all squared plus A over C all squared. Going to do the same two steps. B squared over C squared plus A squared over C squared. Good workout with a little bit of algebra. Those are over a common denominator already. B squared plus A squared over C squared. For any right triangle. So for any angle B, you calculate the sine of B and you square it, and you calculate the cosine of B and you square it. That's going to correspond to some right triangle doing this exact calculation, and because that's a right triangle, Pythagoras says that's just c squared over c squared, and that's equal to 1. And I need an equals here. Okay. And so the upshot is that, I'm just going to summarize it, that whenever you take any angle, and you actually even get a little bit more general with sine and cosine than we do in this class eventually, but even then, it's still going to be true. It's always true that the sine of b, the square of that, and the cosine of b squared, it has to be the same angle. That's really important. But when you square those numbers and add them, they all is equal to 1. And this is really just a version of Pythagoras, but that applies to these functions, these quantities, sine of an angle and cosine. And that's a very profound thing, and you use it many, 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 many times from now on. And if you're following the sequence I'm imagining for my class, that gets used in the law of cosine's derivation right away.